This is the first of a two-part video series discussing work as it relates to mathematics. In this first video, we'll be talking about different definitions that you'll need to know from physics. Then we'll talk a bit about mass density, and then we'll talk about Hooke's law and how it applies to spring systems. You need some understanding of these physics terms, or you will not understand the material in this particular section of the textbook. If you've already taken some calculus-based physics, then you probably already know these terms, and this will simply be review, and also will give you an idea of how we think about these values as it relates to mathematics. We're going to be studying the amount of work done by a force when it moves an object through some non-zero distance. In order to do that, we'll start with the definition for what a vector is. We'll be studying vectors a great deal in Calculus 3. We've already talked about vectors some when we talked in Calculus 1 about velocity and acceleration and position. A vector is a quantity that has both magnitude and direction. They are often represented with arrows on graphs, and the length of the arrow represents the magnitude, and of course the direction is represented by the arrow. We can think of velocity as being a vector because when we talk about how fast we're traveling, 60 miles per hour, we're really talking about the speed. But if I say 60 miles per hour north, then I'm giving both the speed, which is the magnitude, and the direction, which is north. We can also think of acceleration as being a vector and position as being a vector. We can say that I'm 30 miles from some location, and that's my magnitude. But if I say that I'm 30 miles south by southwest of the location, then I'm also giving the direction of my location. In this sense, position can also be a vector. Let's contrast what a vector is with what a scalar is. A scalar is a quantity that has only magnitude but no direction. For example, in the examples I just gave, when I'm talking about speed, speed is simply a scalar, 60 miles per hour. It doesn't indicate which direction I'm traveling the 60 miles per hour. Likewise, my distance from a location, 30 miles, doesn't tell me in which direction I'm located. All constants are considered scalars. Quantities such as force, work, velocity, acceleration, and position are vectors in physics and in mathematics. We're not going to worry too much about the direction aspect of it here in Calculus 2, but in Calculus 3, it forms a core part of what we study. Let's now talk about what mass is. When we think about mass, it's basically the amount of substance that makes up your body. It's really a measure of the atoms and molecules in you. Mass can be measured in kilograms or grams. In the English system of measurements, we don't actually directly measure mass, although there is a unit for mass in the English system, which is actually called a slug. And no, I did not make that up. A slug is the amount of mass that is accelerated 1 foot per second squared when a force of 1 pound is exerted on it. You will see slugs in a few rare applications, but it's far more common these days to use the metric system when we're talking about measuring mass. Then we will see it measured in kilograms or grams. What about density? Let's take a look at what density is. When we're talking about density, we're measuring the amount of mass in an object per unit of measure. Now, it depends on the object as to what the unit of measure is. If we think of something like a very thin wire, we think of it as basically being more or less one-dimensional. When we think of it as being more or less one-dimensional, like a wire or a string, then we would express the density as mass per unit length, which in the metric system would be kilograms or grams per meter, or perhaps grams per centimeter. That would be a measure of the density. We use the Greek letter rho to represent density. Although it looks like a P, it's really the Greek letter for R. In the case of a really thin sheet of material, which we call a lamina, We can think of it as being two-dimensional, like a sheet of paper. In actuality, a sheet of paper is actually three-dimensional. It's a box, believe it or not. It has length, width, and depth to it. If, however, the depth were infinitely thin, we would call it a lamina. In that case, since it has only area and not volume, we would express the density as mass per unit area, or kilogram per meter squared. You could also measure it as gram per centimeter squared. We will be studying laminas here, and of course lamina is the root word for laminate or laminate, which is a thin coating of something applied to a flat two-dimensional sheet. For three-dimensional objects, we typically express density rho as mass per unit volume, often kilograms per meter cubed, or even grams per centimeter cubed. In other words, it depends on the object you're talking about as far as how we're going to measure the density. For a string or a thin wire, we'll measure it in mass per unit length. For a flat two-dimensional surface, like a lamina, which is often infinitely thin, or thought of as infinitely thin, we'll measure it as mass per unit area. For a three-dimensional object, which is most of what exists in the real world, we'll think of it as mass per unit of volume. The density of water is going to come up in a lot of our homework problems, and it is equal to 1,000 kilograms per cubic meter. We don't really use mass much in the English system, so it doesn't have a true density. It does have what's called the weight density of water, where weight is a measure of the gravitational force on the mass of the water. The weight density of water is 62.4 pounds per cubic foot. Basically, what this means is that if you had a 1 cubic foot cube, it would weigh 62.4 pounds on Earth. And essentially, this is on Earth at sea level. If it were up on Mount Everest, it would weigh slightly less, since the gravitational force would be less at the top of Mount Everest than it is at sea level on Earth. That's not truly density, that's weight density, an effect of the force on the density or mass of the water. This representation here in the metric system is truly the density of water, 1,000 kilograms per cubic meter. In other words, we're going to be taking a look at how to measure the mass of something by looking at its density. If it's a one-dimensional thing, like a wire or a piece of string, we can find the mass by taking the density per unit length and multiplying by the length of it. If it's a thin laminate, like a sheet of paper or something that can be thought of as infinitely thin or close to infinitely thin, we can find the mass by taking the density per unit area and multiplying by the area. If we're looking at something that's truly three-dimensional, we can find the mass by taking the density per unit volume and multiplying by the volume. This only works, of course, if the density of the object is uniform, by which we mean that it's a constant throughout the object, that at every point in the object, the density remains the same at each point. On the other hand, if the density varies, such as when you have different parts of the object made of different materials, then you're going to need calculus. For example, let's imagine that we have a thin wire, and one end of the wire is made of tungsten, and the other end of the wire is made of lead. Lead is much denser than tungsten, and so we would expect the density to vary as it changes material from tungsten to some mixture of tungsten and lead, and then eventually to solid lead. Let's take a look now at the one-dimensional case, which is an infinitely thin wire. Let's suppose that in this infinitely thin wire, the density depends on the position in that infinitely thin wire. In other words, one end of it is made of some material and the other end is made of something else. So how dense the wire is depends on where in the wire you are. How can we find the mass? We know that the density varies from one end of the wire to the other, so the formula is the integral of the density function rho of x times dx integrated from a to b. How do we get this formula? We're taking the wire, which you can see here in the bottom picture, and we're chopping it into tiny little sections. Across each section, if we make them small enough, we can assume that the density is constant on that tiny section. And then, if we assume the density is constant, we can simply multiply that mass density by the length of that tiny little section. Then we add up the masses of each of the small little cuts. Sounds like a Riemann sum, because it is a Riemann sum. Again, we're taking the density of each small section and evaluating the mass at a particular point by multiplying the density at that point by the length of that small cut. Then we add up all the small cuts and take the limit as the number of cuts goes to infinity and the lengths of the cuts go to 0. Let's take a look now at example 1. Consider a thin rod oriented on the x-axis over the interval from 1 to 3. If the density of the rod is given by rho of x equal to 2x squared plus 3, what is the mass of the rod? Clearly, the density depends on where in the rod you are, or where along that thin wire you are, since the density depends on x and the length is given by x. This means that we need to set up our integral to integrate from 1 to 3 over that interval of rho of x times the differential dx. This gives us the integral from 1 to 3 of 2x squared plus 3 dx. Pause the video here, work out the calculus, then turn the video back on to compare your answer to mine. You should have gotten 70 divided by 3. Now, we won't be able to handle the general variable density case in 2D or 3D until we have calculus 3. We can, however, consider one special case in 2 dimensions, which would be a flat disk with radial density. Let's talk about what a flat disk with radial density is. When we say a flat disk, we are talking about a lamina, something that is so flat that you can consider it to be 2-dimensional only, and that it is, for all practical purposes, infinitely thin. If we give the density in terms of mass per unit area, something with radial density has density that varies only along the radius. In other words, as we move out along the radius, it either gets less dense or it gets more dense. When we're looking at these, we can think about different metals as having different densities. This might be something that was created in rings coming out from the center, where each ring is composed of a different metal. Tungsten is one of the thickest metals that we have, one of the most dense. It's even more dense than lead. In fact, gold, believe it or not, is actually quite dense as well. Aluminum is not dense at all. So let's say that we start with something that's tungsten in the middle, and then gold, and then it goes outward to lead, which is less dense than gold. And then on the outer ring, we have aluminum. So as we're moving from the center to the outside, each ring made up of a different material becomes less dense. If we let rho of x represent our density function and we put the center at the origin, then we can think about each one of these as a partition, and we can move along the x-axis, and we can create basically a partition going along the x-axis by thinking of each ring, which is centered at the origin, as having roughly a different density moving out from the center, but staying on the x-axis. This makes the calculations more simple. These ring shapes are called annuli, annulus for singular. Let's take a look at the mathematics behind this. If the radii are super close together, then we can consider the density on one particular annulus to be roughly constant. The area of the annulus is given by pi r squared of the outer part minus pi r squared of the inner part. Since we have x sub k for the outer one, and again, this is based on dividing it up into different rings, we have an x sub k here and an x sub k minus 1 there. Then this gives us pi times x sub k squared minus x sub k minus 1 squared. This is the difference of two squares, which can be factored as you see here. Then we can think about the fact that x sub k minus x sub k minus 1 gives us delta x. This portion of the formula is representing the change in the x variable. As the annulus gets narrower and narrower, we can approximate x sub k plus x sub k minus 1 with twice some value that's in the center of that annulus. Now we can replace this in the formula and say the area is roughly 2 times this x sub k star times delta x times pi. In other words, the mass then will be given by the mass density multiplied by the area. Now we can sum over all of the annuli in our partition and take the limit to get the total mass. This gives us total mass as the limit of a Riemann sum, which is the integral integrating along the radius from 0 to r of 2 pi x rho of x dx. Let's take a look at example number 2. In example 2, we have rho of x equal 3x plus 2, representing the radial density of a disk. We want to calculate the mass of the disk of radius 2. In order to set this up, we're going to integrate from 0 to 2, since that's our radius value. Then we're going to have the formula, which is 2 pi x times rho of x dx. By putting in the formula for rho of x, we have 2 pi x times 3x plus 2 dx, integrated from 0 to 2. Pause the video here, work out the algebra and the calculus, then turn the video back on to compare your answer to mine. You should have gotten 24 pi for the mass of this particular disk. Since it didn't give units, you can assume that perhaps they're kilograms or grams, but it is the mass. Now let's take a look at some more definitions that we'll need as we continue our work in work. Let's talk about what weight is. Weight is the force exerted on an object due to gravity. In the English system, this is what we measure when we measure pounds. We're not measuring mass, we're measuring the gravitational force on the mass. The more mass an object has, the more force is exerted by gravity and the greater the weight. You already know that. Basically, your mass is the same since it's the number of atoms and molecules that make up your body, whether you're on Earth, the moon, or floating weightless in the vacuum of space. However, your weight will be vastly different in those situations. You weigh much less on the moon than you do on Earth because the moon is smaller and has less gravity. It has less mass, which allows it to exert less gravity than the Earth does. You weigh nothing at all in the vacuum of space, but your mass is the same as it is on Earth. Let's now talk about acceleration. Acceleration is a vector expressed as a change in velocity with respect to time. It is most often measured in feet per second squared or meters per second. This means a change of feet per second for every second that continues, or a meter per second for every second of change. Gravity is measured by its accelerative force on an object. In other words, we think of gravity as an acceleration. There are two units that we use for gravity on Earth: 32 feet per second squared, which is the English system, and roughly 9.8 or 9.81 meters per second squared in the metric system. What does this mean? 32 feet per second squared means that the first second you fall 32 feet in that 1 second. In the second second, you fall an additional 32 feet per second faster, or 64 feet per second. In the third second, you fall even 32 feet per second faster than in the first two, or 96. For each second of fall, you fall an additional 32 feet per second faster than you did in the previous time period. This is only true up to a certain point because our atmosphere has air molecules in it. These air molecules will slow you down and you reach what's called a terminal velocity, meaning that you can't fall faster and faster and faster. If you were falling in the vacuum of space, however, you would fall faster and faster if, of course, there was some gravitational force on you. Let's think about what this force is thought of. It's a push or a pull on an object resulting from the object's interaction with another object. It can be measured in different units. In the metric system, force is usually measured in newtons, capital letter N, named for Sir Isaac Newton. A newton is a kilogram times a meter divided by seconds squared. It's often written as kilogram meters per second squared. You'll see it S squared, but you'll also see it sometimes written as SEC squared, which still stands for seconds and not secant. What are some other ways that we can measure this? Let's talk about Newton's second law of motion now. Sir Isaac Newton has 3 laws of motion, and his second law of motion states that the force acting on an object is equal to the mass of the object times its acceleration. In other words, the more mass, the more force is required to get it moving. The mass times the acceleration gives us the force. Greater mass, greater force. Greater acceleration, greater force. Work, on the other hand, is the force exerted or applied through a non-zero distance. Work can be measured in many different units. In the metric system, it's a joule, which is the same as a Newton meter. Thus, 1 joule, which is 1 Newton meter, is 1 kilogram meter squared per second squared. Let's write out what these look like. 1 joule, which is an uppercase J, since it is also the name of a person, is equal to 1 Newton meter, which is usually written hyphenated, which is equal to 1 kilogram meters squared divided by seconds squared. Remember that a Newton is a kilogram meter per second squared, and when you move this force through a distance, you are adding an additional unit of meters. There are other units that we can use for work as well. Work can be described in ergs, which is 10 to the negative 7 joules, or electron volts, which is even smaller. The horsepower hour is given here, which is also a measure of work, or the kilowatt hour in the liter atmosphere. There are lots of different ways of expressing work. In the English system, work is expressed as foot-pounds. A foot-pound is roughly 1.36 joules. If the force cannot move the object, then no matter how much energy is expended, zero work is done in the physics sense. This means that no matter how hard I push my car, if I don't move my car, then I've done no work. What I really mean is I've done no external work. I have done internal work inside my body because my muscles have been working. But if the car doesn't move, then as far as physics is concerned, I've done no work. Work can be written as the force being multiplied by the distance through which the object is moved. Since force can be written as the mass of the object times the accelerative force, we can write it as mass times acceleration times distance. This assumes, however, that the force is constant, which it may not be. In fact, it often is not. If the force exerted depends on where the force is acting, then it becomes a function of position, which we can write as f of x. To compute the work done when the force is not constant, we will again divide the distance into tiny intervals. Since each interval is very small, we can assume that the force over that small distance is roughly constant. Then we compute the work using this formula here, where over that tiny interval of distance, the force is constant, and we can write F times d equals work, or mass times acceleration times distance equals work. Then we compute the work on each subinterval and add all the works together. Then, of course, Since this is a Riemann sum, we take the limit of the sum. Let's look at the formula that we get from doing this. In this case, the work done by the force in moving an object from x equal a to x equal b is given by the definite integral from a to b of f of x dx. This is for a variable force where the force depends upon the position. Now we want to talk about springs. We're not going to spend a lot of time talking about springs, but we will cover the basics here. In your physics class, you will probably spend a lot more time talking about springs and Hooke's law. John Hooke was a Scottish mathematician who spent a lot of time looking at the dynamics of springs and studying the force, the accelerative force, and the mass and the work done on a spring system. Springs form a big part of all kinds of machinery, and this is one of the reasons they come up so often in physics. There are lots of different kinds of springs, and I have pictures of several of them here. We're going to be looking at what's called a constant rate or linear rate spring, where the coils are all the same size from one end to the other, and they're wound with the same amount of tightness from one end to the other. Not all springs look like that. You can see over here that in this type of spring, the coils have a smaller radius at one end than they do at the other. There's also something called a progressive rate spring, where the springs become tighter coiled, though the radius stays the same, but they get tighter and tighter as we go from one end to the other. You can also have what's called a dual rate spring, where it's an abrupt change and not a gradual change as in the progressive rate. We're going to be focusing on the constant rate or linear rate spring, which is what you see here and here, also in the tension spring and in the compression spring. Let's take a look now at what some of the formulas are for springs. Each spring has a natural length called equilibrium. This equilibrium length is when it's at rest and it's not being acted on by an outside force. In other words, it's just sitting there on the table. Nothing's hanging from it, nothing's compressing it, it's just sitting there. That would be the natural length or the equilibrium. To compress it takes effort, to stretch it takes effort. When it's just sitting there, it's at equilibrium or its natural length. When we draw this, we can represent it in the picture here by attaching the spring to a block on the left, which is shown in blue. We attach the other end of the spring to a movable block shown here in the tan color. At equilibrium, the block is not moved and it's just sitting there. To compress the spring, we have to shove towards the fixed block in blue. This requires energy or force to do this. To elongate or stretch the spring away from equilibrium also requires force and energy to accomplish. Let's talk now about Hooke's law. Hooke's law is the force required to compress or stretch the spring from its equilibrium position. It's given by f of x equal to kx for some constant k. K is called the spring constant, and it depends on physical characteristics of the spring, such as the material that the spring is made out of, how tightly the coils are wound, the radius, and the thickness of the wire. The thicker the wire and the more dense the material, the more energy it takes to compress or elongate it. The constant is always considered to be positive and is dependent upon each spring, the type of spring, the radius of the coils, and the thickness of the wire. Let's take a look now at example 3. Suppose it takes a force of 8 pounds to stretch a spring 6 inches from the equilibrium position. How much work is done to stretch the spring 1 foot from the equilibrium position? First, we need to find the spring constant K. We're going to draw a picture which represents the first sentence. Let's picture our immovable block on the left here in blue. Then we have this spring coming out from it attached to another block at the other end. When we attach it to the other block and it's sitting at rest, this would be at equilibrium. And we can consider this location here to be x equals 0. Now we want to know what happened when it got moved 6 inches beyond the beginning place. When it got moved 6 inches, it was stretched, which means that it got stretched out like this and has moved beyond. The distance now is 6 inches. However, in the second sentence, they use a measure of 1 foot. We're going to have to pick inches or feet, and we typically pick feet. In other words, this distance right here is now at x equal half of a foot. The force that was given to accomplish this was 8 pounds. This does not mean that it was 8 pounds at every single point. This is an average of 8 pounds, as if it were applied at every point. Probably it took more force to get it started moving and less force after it was moving. It would take more force towards the end because you're stretching it longer and longer. The real force to stretch the spring is a variable force, but the force that's given here is an average value. That means that we can use it in Hooke's law, which is F is equal to K times X, to find the spring constant. We take our average force of 8 pounds and we set it equal to the spring constant K multiplied by the distance that was moved, which is half of a foot. We can solve for K then by taking the 8 pounds and dividing by half of a foot. This gives us a value of 16 pounds per foot. This is the spring constant K. Now let's imagine what happens for the second sentence. How much work is done to stretch the spring 1 foot from the equilibrium position? Starting back at equilibrium now, we see the immovable block on the left, and now it has been stretched even more so that it's going out here to a distance of 1 foot from equilibrium. The question is, how much work is done to do that? Again, the real force needed to stretch the spring is a variable force. It requires some force to get it moving in the first place, then less force as it starts to move, then more force as you stretch it longer and longer past its equilibrium. We're looking for the work done. In order to find the work done, we need to integrate since we have a variable force. We're starting at equilibrium, which is x equal to 0 feet, and we're going out to x equal to 1 foot. Our force is variable, meaning it's f of x, and we're dividing it into small pieces. Now we can take the formula for each small piece where we're assuming that the force is roughly constant and use Hooke's law to replace f of x with kx. This then gives us the new integral x equals 0 feet to 1 foot of 16 pounds divided by a foot times x dx. This is coming from Hooke's law. Go ahead and pause the video here, work out the algebra and the calculus, then turn the video back on to compare your answer to mine. Notice that we leave the units on the limits of integration. When we integrate x, we get x squared over 2, and the 2 and the 16 reduce to 8 pounds per foot, multiplied by 1 foot squared minus 0 feet squared. This gives us 8 pounds per foot times 1 square foot, or 8 foot-pounds of work. Let's now move on to example 4. For the same spring system as in example 3, how much work is done to stretch the spring 4 feet from the already stretched 1 foot position? Keep in mind that you must do more work to pull a spring that's already been stretched even further than there is required to pull the spring from an equilibrium position. Pulling on a spring that's already been stretched is much harder than pulling on a spring that's at equilibrium. For this one, we're going to draw a picture now that you can see here. At equilibrium, it is here. Ours is already stretched to 1 foot, which means it requires force to maintain it there. Now we want it to stretch even further from 1 foot out another 4 feet to 5 feet. In other words, we're moving from 1 foot here out to 5 feet out here. This means that when we set up our integral, we'll be integrating from x equal 1 foot to x equal 5 feet. This is not the same thing as integrating from 0 feet to 4 feet. Starting at 0 feet is starting at equilibrium, and it would require less work to go from 0 to 4 feet than it does to go from 1 foot to 5 foot, even though the distance is the same. That's because it requires more work to stretch an already stretched spring. Then we have our spring constant times x, that's kx for Hooke's law, times the differential dx. On each small partition, we assume that the force is roughly constant, which is how we use kx. This, of course, then gives us the integral from 1 foot to 5 feet of our 16 pounds per foot, which is our k, times x dx. When we integrate, we get x squared over 2. The divided by 2 reduces our value to give us 8 pounds per foot. Then we have to multiply by the square of the limits of integration. 5 feet, quantity squared, minus 1 foot, quantity squared. We'll end up with square feet for this unit divided by feet, which will give us the foot-pounds in our result. When you work out the arithmetic, you'll find that you need 192 foot-pounds of work to accomplish this. If you were to integrate from 0 to 4 feet, which is the same distance, you would find that it requires less work since you're starting from equilibrium. This is the end of the video, which is an introduction into work, looking at definitions and springs. In the next video, we'll be looking at the work done in pumping liquids out of a tank or a container, or in lifting liquids out of a tank or container.